Okay, good evening. Welcome to the TAAA monthly meeting. The Tucson Amateur Astronomy Association meets here at Stewart Observatory's auditorium the first Friday of every month. We're glad you could join us. I'm Ed Foley. I'm the president of TAAA. We've got members here in the room with us. We've also got members on Zoom, and we've got folks joining us on social media tonight. So we've got a big group. We have a number of speakers tonight. We also have some interesting challenges. We've got some new technology. We've got a whole technology team here today. We've got Jim Knoll at the helm with the new camera. So we're going to see how this works. It follows the speaker. And of our speakers, I think our first speaker, Dr. Mary Turner, is among the most mobile of speakers that we have. So she's going to be a particular challenge. We'll see how that goes. Mary, just try and stay in the spotlight. Like I say, we've got a number of presentations tonight. We're going to start with our chief observer, Dr. Mary Turner, who will give us her quarterly What's in the Sky report. We'll know what we have to look forward to here for the next quarter. And Mary, please tell us what's in the heavens.
Thanks, Ed, and thank you for inviting me back. It has been a while. Hey, don't follow him. I'm the speaker. Okay. So again, since this is the last month of the quarter rather than the first month, no problem. You all know I'm incapable of standing still, so we'll work through this together. So since we're sort of the last month of the quarter, I sort of have some things that you can see this month and also into next month as well. And we'll take a look. And you'll notice that it's definitely a fishy sort of month. And when we go further on, I'll explain why. Well, I'll tell you now. You're all familiar with the concept of gravitational lensing, okay? And you all know I'm a physicist and an engineer. It's some weird combination of the two, and that I work with other engineers, physicists, and weird combinations of the two. And we saw an image the other day, and it was of one of the galaxy groups that are within Pisces. It was an amazing picture with 7 or 8 different galaxies that were being lensed gravitationally. So you had those little things all over. And so then we got into discussion, since the latest project I'm working on is an imaging system to help generate entangled photons. So we were sitting there saying, okay, well, what if Alice is in this building right behind the optical sciences, and she has her little box with her photon in it? And Bob is in a galaxy far, far away, and he has in his little box the other entangled photons. And when the information between those photons goes and gets gravitationally lensed, does that affect the actual quantum state? And would those photons still be entangled? And it's like, yeah, you want to make sure you keep your engineers busy, or they go off on all sorts of weird tangents. But, hey, it's Pisces. I haven't talked much about Pisces. There have to be other things to think about in Pisces. So that's the tangent I went on, and that's why it's going to be rather fishy. And we never did decide what the answer to what happens when photons get gravitationally lensed when they try to go back to the coupled pair. But, I digress. I do that a lot. You probably all know that as well. But here are several objects that we're going to talk about within the Pisces constellation. And of course, we will start with a little bit of the legends, lore, myths, legends, and downright lies associated with that constellation. How many of you believe anything associated with any of those stories about the constellations? I'm with you. I mean, there's got to be something to the fun, and a lot of it does have to do with effectively keeping calendars, so that's important. But here's a little sort of star chart from the sky of the constellation, showing how obviously those stars look like nothing other than a pair of fish tied together with a string. I could just look at that, and that when I saw those lines, that's what said. That looks like two fish tied together with a string. Absolutely. What were they smoking? That's all I'm going to say. However, even though it's, may not be quite as obvious to us, several different cultures, not just those descended from the knowledge of the Babylonians, had the same type of model associated with those stars. So there's got to be something to it. And of course, here's another little model of it as well, sort of. Might as well add a little bit of color. Sky only adds turquoise and white and black, so it's sort of boring. Okay, so let's talk a little bit about the mythology. If we start with Greek mythology, now, yes, the Greek mythology all came from the Babylonians, and then it became the Roman, but all the Romans did was change the names and the places a little bit. But if we look at the basic mythology, it was that we had Aphrodite and her son Eros that jumped into the Euphrates River and turned into fish. And I think, when they two got together, tied themselves together and jumped into the river and wanted to turn into fish, it would be sort of reasonable to ask why they might possibly want. I'm not, I can't help it. Okay, why would they want to jump into the river? Well, it goes back a couple of generations. Okay, we all know the mythology between, the gods and the Titans. And the Titans were defeated by the gods. And the Titans were the parents, if you will, of the gods. But where did it all come from? Well, it all started with Gaia, Mother Earth. And so when the gods defeated the Titans, it was effectively Gaia's grandchildren ganging up on her children and, taking them out. And for some reason, she wasn't overly happy with this. The thing about Gaia was some of her children were the Titans, but she had a lot of them, and some of them were not, shall we say, quite normal. Okay, none of them were quite normal, but some of them were less normal than others, one of whom was Typhon. And he was a snake that had 100 dragons' heads. And that, she felt, was the perfect way to avenge the loss of the Titans. Now, it does seem a little perverse, though, sending a monster out to eat your grandchildren when most of them were actually eaten by their father in the first place and had to be disgorged. I guess it's history repeating itself. I love this stuff. But basically, the Typhon was going after Aphrodite, and she, in order to save herself and her son, she basically tied themselves together with a long string so they could jump into the river and pleaded for Zeus to turn them into fish. He did, and they swam away safely. And I did fat finger spelling Zeus, but I know how it's supposed to be spelled. Surprised that Microsoft didn't pick that up, although spell checkers leave a bit to be desired. There are several variations of the same theme, but basically, Aphrodite and her son Eros jumped into the river to evade Typhon, and therefore, after their death, they were given a position in the sky. Okay, now obviously the Romans followed the Greeks, and so the story was just fine. They just wanted to use Venus and Cupid instead. Again, simply changing the names. It all started, of course, with the Babylonians and the Assyrians, etc. Same group, same area. They were part of a pair of constellations, the Swallow and the Lady of the Heaven. I see those even less than I see the pair of fishes. But that also was slightly larger. It did include part of what's now part of Pegasus. And the Lady of Heaven was the northern fish as well as part of Andromeda. And then, of course, there was the fish cord in between them. So I guess that cord must be really important. And within the Babylonians, each zodiacal constellation covered about 30 degrees in the sky. Although the Pisces constellation, you know, first glance doesn't look overly impressive, not too many bright stars, only one Messier object. It does actually cover a fairly significant portion of the sky. And again, even going into Persian lore, so going closer towards the Middle Ages, same type of Venus and Cupid who tied themselves together so they didn't get swept apart when they entered into the Euphrates. The particular star that one of the stars we're going to talk about is Alpha Piscium, and that's the one at the base of the V, if you will, which represents the knot of the rope. Okay. Oh, that's the wrong button. That's the other button. Okay. I like the German legend. It's sort of fun. And Tenta owned nothing but a wooden tub and a rundown cabin. He happened upon a magical fish. I wish I could happen upon a magical fish or a genie's lamp, something like that one of these days. We could always hope. And the fish offered to grant him whatever wish he wanted. Okay. And he said, no, I'm fine. I like what I got. I'm happy. I'm satisfied. But, 3 hots and a cot. What more do you need? Told his wife about it. She was not overly pleased about this situation. Somebody offered to give you anything you want and you didn't think about something for me. Okay, so I'm editorializing a little bit. So she sent him back, obviously, to ask for a new furnished house. Okay, and the fish said, fine, deal's a deal, gave it. So she now had her nice, fine, brand new furnished house, and of course she was now unsatisfied. She now wanted to be made a queen, and her house had better be a palace. And it's like, fine and dandy, until the next step up is to be a goddess. And as we all know, the one thing you don't do to the gods is try to make yourself equal to them. They sort of take that personally. But I will give the magical fish, credit. Normally, when you step on the toes of the gods, they smite you. The fish just took away everything and left them with their rotten house and their wooden tub. Maybe that was worse than smiting them down. Who knows? But again, there's always a little bit of fable to some of these stories. From some locations, the knot in the cord looks to be below the ecliptic. So it therefore becomes the underworld, where you have one fish positioned to escape and the other is being drawn towards the dark side. And then if you combine that with Cetus the whale, you have the basis for that final labor of Hercules, which I haven't talked about in a few years, to capture the head, the Cerberus, the monster that guarded the gates of Hades, who also was the son of Typhon. So you can tell the generational change, sort of, if you are, for example, Irish used to have a lot of red-headed people, but not so much anymore, because you intermarry, and each generation you have, less and less chance of having red hair because it's a recessive gene. So Typhon had 100 dragons' heads, but his son only had 50. So. And that's preparation, because later on I actually do math in this talk. What? Did I do something? Oh. Okay, so first object we're going to talk about is Alpha Piscium. I like that one, Piscium. That's much softer than some of the, it just rolls off the tongue. There are some of them that get a little bit more complicated. It is a variable star. Don't plan on looking out and say going out in your backyard and looking at it and say, oh, look how it's changing. It changes like ballpark of 1% total. You sort of need to measure it, but it is extremely cyclic. And there is over a 17-hour period. That's what it looks like. But again, just look at the scale. This is about, so 1 is obviously maximum, and it goes down to just below 99% of that. So we have other variables that are much more noticeable, but this does have a very nice cyclical pattern. And here is sort of what it would look like in your telescope. And at one point in time, I was able to get a laser out of here, but I'm not sure. Oh, underneath. Oh, that's why I got it, because it was accidental. Okay. So here is the region here. And if you isolate in on it, you can see the separation because it is a binary star system. I got to get the right button, the correct button, which actually is the right button in this particular case. Okay, so a little bit about Alpha Piscium. It's also called El Resha, which from the Arabic means the cord. Sort of makes sense, although it's technically the knot. Visual brightness is 8.32 because it's made up again of the 2 different components. They are separated by a little less than 2 arc minutes. One of them is a spectroscopic. I work with those machines all the time and I still can't do it in that form. Spectroscopic binary, they also both might be, which means there's at least one other star there, but it's too close to visually separate, but you can get because of the color information that you can derive. It's also what's called an alpha squared Canum that's not as, doesn't roll off the tongue quite as well, Venaticorum variable. And the brightness is changing as a function of this rotation of the star. The period of the rotation of the primary and the secondary is about 3,300 years. Star group is about 180 light years away. Total mass is about, of the alpha star, the A star is about 2.6 times that of our sun. And the radius is also about 2.66 times the sun. So pretty much, 2.5 times the size and weight of the sun. It is, however, about 10,000 Kelvin. It's a hot little puppy, sort of white-blue type. And its luminosity is obviously also significantly more, since it's burning much brighter. It's about that of 63 times the sun. Okay. Next one is Eta Piscium. And it's another double star, but it's also it's a giant star as well, so much larger. That's right underneath. This is the star, and just for reference, this is the only Messier object, M74 in Pisces, but we'll be talking about that later. But if you can find M74, you're in the ballpark of Eta star. Chances are, though, you'd find the Eta star and then find the 74, the galaxy afterwards, because it is a bright enough star to see. Ra and Dec. Okay, so a couple of names to it. Historically, so long term, starting with the naming by the Arabs, in let's say 13th, 14th century. It was called Kulat Nunu, which means cord and fish. The Nunu is the fish, the Kulat is the cord or a barrel. How something can be either a cord or a barrel, I'm not sure. Now the officially granted name to it is Alfurg. Why would you trade Kulat Nunu for Alfurg? Total brightness is about 3.6. Obviously, in this particular case, the B star is much dimmer. Interestingly low, if you remember, that's a little bit lower than the previous one. So although this is the Eta star, and we previously talked about the Alpha star, in this constellation, the Alpha star is not currently the brightest. Alpha is, but also it's further along on its life cycle. Angular separation between the A and B stars is about 0.6 of an arc minute. Of an arc second. Burnham just determined that it was a binary, so that was getting close to 100 years ago now, or more. Rotational period of the two stars is about 850 years, about 350 light years away, so about twice as far away as the Alpha star. Mass is less than 4 times that of the sun, which is still pretty hefty, but the radius is 26.5 times that of the sun. And again, it's a giant star. It's already burned through, and it's doing its helium. It's on its helium cycle. Luminosity, 457 times the sun. Okay, so it's definitely a very bright star. It's brighter than Alpha to us, even though it's significantly farther away. And this is probably the interesting thing, 220 million years old. So it started out as a very large, hot star and burned through itself very, very rapidly. Okay, Wolf 28. Don't get to talk about these very often. And this is Wolf 28 over here. This is just a star that's in its field of view. Because finding Wolf 28 on its own without, well, if you know where it's located, you can find it. It's a white dwarf. It's one of the few white dwarfs that we can actually visually see with a telescope. You know, as long as your scope is a daub of at least 8 inches, you're probably going to be able to see it. I would recommend dark skies, but you are going to be able to see it. There are a few white dwarfs we can see, but not necessarily a whole lot of them. Okay, so pay attention to what, oops. Okay, so I said we get to do some more math. Wolf 28 is also referred to as Van Manen star. Again, you're going to be able to see it. It's not one of those impossible objects I sometimes pick because they're really cool and have fun information about them. It's about just under 14 light years away. Its mass is about 1 times the sun. However, its radius is about the same as the Earth. Okay, so might have all heard the expression, a pint is a pound the world around. That's not really true. It's only true in the US because we all define the pint differently. Brits have it better. When they get a pint, their pint has more beer in it than ours do. So, you know, you can look at it from that perspective. But basically, a pint is 1/8 of a gallon, and it's 16 fluid ounces. So pint is a pound, so 16 and 16. If we go into a metric regime, the density of water is 1 gram per centimeter cubed. That's how the metric system is defined, is based on certain basic standards. So if we look at the volume of the sphere, which is 4/3 pi r cubed, and we take the radius of the sun, which is approximately, give or take, 395,508 kilometers. Yes, I could have rounded up to 400,000. The Earth's radius is about 6,371 kilometers, or I could have rounded them both to 3.5 or something. Yeah. Did I transpose that first number? I think I messed up. I think it's 695,508 because they're in relative proportion. But if you take the non-transposed number version and just take the radius of the sun cubed divided it by the radius of the Earth cubed, you get about 1.3 million. which has basically the matter making up Wolf 28, is 1.3 million times as dense as water on Earth. So when people tell you that a teaspoonful of material from a white dwarf, weighs as much as the Himalayas or something like that, that's where that calculation comes from. And when I was playing through it today, I just had to, I'm an engineer, I had to work out the calculation myself. So, and Terry doesn't like it when I do math, so. Okay. So let's talk a little bit about Gamma Piscium. Again, another obviously bright giant star, but of significantly different physical properties than the giant star we just looked at. Keep in mind, if nothing else, the age. Okay, it's a yellow giant. Again, the mass is about about equal to our sun. It's a star that was on the same sort of life cycle as our sun. Currently, the radius is about 11 times the sun, so it's, again, definitely early in its death throes. Luminosity, about 63 times the sun, so relatively much dimmer than the previous star. Temperature is about 4,800 degrees Kelvin, a little bit cooler than age, about 4.5 billion years. So rather than going through that cycle in 220 million years, this one has been around for a long, long time. And its magnitude is 3.7, so it's not quite as bright as the Eta star, but it is slightly brighter than the Alpha star. The other interesting thing about it is it's not really, its chemical composition isn't correct for where it is, okay? The material that it is made up of compared to the stars around it is much lower, which means it was formed in a different place. So it's actually traveling through space, and right now it is where it is, but it's not there. It's moving quite rapidly, like to the ballpark of like an arcsecond a year. So it's going to be in the neighborhood for a limited time. Now, yes, that limited is on an astronomical scale, but again, it's just wandering through the universe, and will eventually disappear. But it'll still look like a fish, trust me. Okay. Again, when you first look at Pisces, it covers a large area of the sky, but it happens to be an area that isn't necessarily filled with, wonders like the Messier objects, although there's a lot of interesting things in terms of galaxies and clusters that go on out there and gravitational lensing. But they do have one Messier, so I obviously need to talk about it, and it is the spiral galaxy M84. And I think most of us who have telescopes have looked at this galaxy. Maybe not quite, it doesn't quite look like this when you're looking visually, but you can capture images. And for every hour you collect photons, you spend 24 hours in Photoshop, and eventually you'll come up with something that looks like that. And this is a Spitzer image that shows, again, as you look at the different wavelengths, sometimes infrared, sometimes X-ray, sometimes a combination of them, you get a lot more detail and structure. So we can clearly see the rings, regions towards the center, black hole. We can't see the black hole, but we can see concentrations of energy and light. I'm sorry, if there's a web picture, I'm going to show it. I'm a taxpayer. You're all taxpayers. We might as well. I mean, I think we're all the same way. The pictures that web takes that we can get from the web are unbelievable. So definitely a lot more structure. You can definitely see that different things are going on all over. There are voids, there are gas clusters, there are regions of star formation. And if we had these pictures first, we wouldn't call them spiral galaxies, we'd call them conch shell galaxies. I mean, look at that structure. That is just so cool. Easily amused, I admit it. So is it looking at me or is it looking at Ed? Okay. Quit moving, Ed. Okay, so again, sort of star map view, R.A. and Decker over there. So it's also referred to as the phantom. It's a face-on spiral galaxy. I love looking at face-on spiral galaxies. Sombrero is fun to look at, but you get so much more when you see them face-on. It's about 33 million light years away. I hate to have to count zeros while I'm looking up. About 10 by 10 arc minutes if we look at it from Earth. So again, obviously a nice telescope object. Actually, that corresponds to about an 85,000 light years from side to side. Magnitude is about 9.4, and those are 100 trillion stars and 600 trillion times the mass of the sun in those stars. Lots of hydrogen too, so there's lots of star formation still going on, or we were seeing the results of star formation still going on, and that was the red. That was all those little zones of red that we can see throughout. All of those are potentially active star-forming regions, or they were active star-forming regions 33,000 years ago. Okay, so the area around NGC 383 is where we saw this picture with all the gravitational lensing that got us set off on all sorts of weird tangents. I won't tell you what we thought about the picture coming in off an interferometer the other day. I'll save that for another time. But it is part of the sky that is defined by Pisces. Yes, this is Andromeda, but apparently Andromeda stepped over the line once or twice, and she's now in the wrong area, at least according to the sky. So, you know, whether you want to look at the end of Pisces or somewhere around Merak and Andromeda, that's where not just this galaxy, but a whole cluster or string of galaxies is located. Definitely a pretty area of the sky, if you like looking at galaxies. Sort of a lenticular, elliptical type shape. And this doesn't do it justice, but I've got another picture coming that is a little bit better. Definitely has gas jets going out on both sides for very significant distances. This is from the Chandra X-ray Observatory. That's what the jets look like more accurately. And they are definitely spreading out very strong, and obviously as they go through space, they're going to dissipate a little, spread out a little, but they are massively long. Here is a picture of that area in space. So this is centered on the NGC 383, but you can clearly see that there are many other galaxies very close by, some of them that are much further distant, but these are actually thought to be linked. They're all independent galaxies, but there are a lot of commonalities between them, and you can see that there are many, many galaxies within this region of space. I like looking at galaxy clusters. It's also referred to as ARP 331, so it's in ARP's list of peculiar galaxies, which basically whatever ARP wanted to say was peculiar is peculiar, but definitely the lenticular galaxy is a little bit slightly different in shape. It's also what's referred to as a radio galaxy. It has high energy jets emitting from them. Usually radio is associated with the term radio galaxy would be associated with radio wavelengths. However, these are also a source of significant X-ray energy as well. So very, very powerful jets. They are traveling close to the speed of light, so it's relativistic movement. Obviously, they're not entangled photons, so they can't be traveling faster than the speed of light. None of that spooky action at a distance stuff. I said the jets were really, really large, at least 20,000 light years. It's about 210 million light years away. Actual diameter of the main body is about 150,000 light years, so that doesn't include the jets. Parent size is about 2.3 by, let's call it 2 arc minutes. And it's the brightest of all of the galaxies within what's referred to as the Pisces chain of galaxies, because there is a very linear positioning to those different galaxies. Obviously, we don't see the depth of that. We only see two-dimensional in a picture. Okay. So, moving on. Okay. Thought I had something else I wanted to say, but I forget what it is, and I'm sort of trying to watch the clock. Not that I ever do that much. So next thing I want to talk about is the double cluster. NGC 884 and 869 will always be my husband's favorite thing to look at in the sky, so I'm going to take the opportunity to talk about it, and we'll talk about this later. So again, come down here, look at the W, and just at the end, head towards Perseus. And to some extent, they're even, if conditions are right here in Tucson, they're a naked eye object. Obviously, you want to look at them through a telescope, you see so much more, but it's easy to find with your telescope because you can see them. Right, okay. And here's one of Michael's pictures of them. And oops, preview. Yeah, so and here. And they are obviously two open clusters that are very closely spaced to each other. Again, it's one of those enjoy them while you can, because obviously open clusters don't have much gravitational effect to bind them together. So all the galaxies are doing their best to pull them apart. But for now, we get to look at them. Okay. Here is obviously more. There's more detail and data in this picture, which I got from SkyMap. It's probably a Hubble picture. They didn't say specific. No, I think it's a 2MASS picture. The 2-meter all-sky survey that UMass did. But you also notice that you really got a lot of information from a little picture, simple picture taken. I'm not going to say in our backyard. I think it was taken in Steve Peterson's backyard. But again, you get a lot of detail here. What we're not seeing in that is the nebulosity, which we can get a little bit of in pictures taken and properly edited, shall we say. Okay. It is, okay, it's his favorite. It's way up on my list as well. What's really great is show kids, because the first concept my mother described when I let her look out through a telescope in our backyard many years ago, we were looking at Hercules. And the first words out of her mouth was, "It looks like diamonds on black velvet." And I love that analogy and I use it a lot. But I think when we talk about looking at the stars and all the stars in the sky, it's hard to conceptualize what that number is. But when you show kids the double cluster and just, you can see that, they're almost countable. That, you're looking at one area of the sky through a telescope and you can start counting effectively hundreds of stars. You're not going to count them all, but you can get an idea of, yeah, in this one region of space, we have many, many hundreds of stars. It's sort of fascinating. Technically, it looks to me much closer to Cassiopeia, but again, they broke the sky down so that it's actually part of Perseus. They're ballpark of 7,000 light years away. One's closer than the other. They're about 300 to 500 light years apart from each other. They're about 12 million years old. They are related to each other. They were formed at about the same time. Again, there are going to be lots of situations in Tucson, at least, years ago when we had clearer skies. It's a naked eye object. I can go out in my backyard and I know what I'm looking. Once I see the M or the W, depending upon how Cassiopeia is laying that night, it's pretty easy to find. There are more than 300 supergiants in each cluster. Each of them is about 60 arc minutes across, so about a degree. And the magnitudes are very similar, 3.7, 3.8 for the two of them. Okay, so now if you happen to be looking at the double cluster and you just want to start to move a little bit out, you can actually see the heart. And I got to admit, I can see a heart here. We all agree? So what do we see here? Pardon? No, that's the fish head. You can't tell that that's the Fish Head Nebula? Seriously? Yeah, and these are basically our star formation regions, so we're obviously seeing lots and lots of gas patches. But again, within the sky, there are so many regions of nebulosity with fascinating shapes and science and history in them, and I'm way too easily amused. Okay, yes. So I'll tell you what, 'cause why don't we give you the opportunity to get him set up and I can stop here. So, okay, if he's ready, then that's fine. I won't take it personally. So thank you all very much. So, I'll let you take over the computer. Oh, did anybody have any questions? Just remember, if you ask questions, for every question you ask is a minute longer, you have to stay here tonight. It's getting cold.
Thank you, Mary. Thank you for that threat. All right. Okay. Lots to see, and you can see that Mary she could go on and on. But unfortunately, we have another topic tonight that we'll have to cut to. We have another member who's going to be joining us, but this member is spending the winter in Hawaii. Oh, well, but he is coming to us through the wonderful means of the internet. And Russ is a very interesting fellow. Dr. Russell Genet has a very varied background. All of you that have seen what was written about him on the email and what we have published on the internet about his background is just tip of the iceberg. He is a jack of all trades, obviously passionate about astronomy, but what I think you'll get is that he's also passionate about education. He spends a lot of his times with students, helping students to learn how to learn. And Russ has been learning for a really long time, continues to learn, and he's going to teach us a little bit tonight. And do we have him? We have him. Okay. All right. Russ, if you'd unmute,
Yes. Can you hear me yet?
share your screen and
Okay,
join
I
us.
will share the screen.
Okay.
Oh, we
here he
need to make
comes.
sure we turn on the,
Welcome. There you go, Russ. Take it away.
okay, I do need to make sure we have that audio, sharing the audio, see how I can get back.
We're not hearing you, Russ.
Okay. Testing one, two, yeah, okay.
We're still not hearing you yet.
Hmm. Well, let me change speakers.
Oh, interesting. We have a message on the screen that someone on Zoom hears Russ, but we don't hear Russ in the room.
Testing. Can you hear me any better?
Okay, we have two people saying they can hear you, Russ. We just can't hear you in the room. We're working on it here.
Okay.
We do have some new technology today that just bear with us.
Okay. I'll bear with you.
We're just taking a minute to look at the manual. Okay, Russ, try saying something again. See what's
Okay, I can keep talking here. So you can see when it comes up.
we're just changing the volume now. Let's see. We do seem to
Okay.
hear something.
So I can see Frank there. Frank, can you hear me in Australia?
We can
Yeah.
hear you now. Thank you, Russ.
Oh, you can hear now? Ed, did you say you can hear now?
Yes, we can hear you.
Okay, great. Well, I'll get rolling now. Okay, so I want to talk about it's kind of a 45-year story. At any rate, it's how a bunch of amateur astronomers developed robotic telescopes and together with students observed binary stars with ever increasing, ever smaller separations between the two stars and shorter orbital periods. And in the process, over a dozen books were published and over 200 team papers. And this is amateur astronomers teaming up with students. And at any rate, that's the story I want to go over. And let me see if we can advance the slides here. So the story kind of starts at when I was a research and development supervisor at Wright-Patterson Air Force Base, and actually in 1979. And so I had a bachelor's in electrical engineering. I didn't have a PhD in astronomy at that time. And I wanted to just do some scientific research as a hobby. And astronomy looked like a good hobby, but I wanted to publish my research, in a good journal. And so I looked through the library at the Air Force Institute of Technology. They had 5 years of the Astronomical Journal. They subscribed to it. So I looked through 5 years of it, asking myself, could I myself, with my budget and so forth, have done this research? Well, usually the answer is no. They were observations on a 100-inch telescope, or they were advanced theory that was really quite beyond me. But there were about 30 papers that were observations of photoelectric photometry of variable stars. And most of them, of those papers, were with 16-inch telescopes at Kitt Peak National Observatory. So I kind of figured, well, if they could do it, I could do it. And so on the left there is it's actually a one-page advertisement from Scientific American, and it shows my first telescope and setup. So it was a 12-inch cast grain telescope that I designed and built myself. You can see it's got a little bit of a jury rig. I'm dyslexic. I have a real problem doing arithmetic and spelling. And so I bought a TRS-80, the Trash 80 that some of you older folks might recognize, to do the data reduction, because it's not complicated, but it's just there's quite a few calculations, and I wouldn't have gotten them right. And so that was my initial setup. And the TRS-80 actually had to stay in the study. It was environmentally not very rugged, and so it was just put out in the observatory for this photo op, if you will. And but at any rate, it was fun, but a little bit science can kind of be a little bit boring. You're observing the same thing over and over and repeating, trying to get your noise down by repeated observations. At any rate, I was interested in, well, let's see what else we can do with this computer. So the first thing I did was replace the strip chart recorder, which it took lots of time to take the data off of the strip chart recorder. You have to measure it and then enter it in the computer. And so the idea was just take the data directly off the photomultiplier tube on the photometer and into the computer. And then I said, well, maybe get stepper motors to control the filter wheels, and then I was kind of staying up late at night, and the wife and my boss were wondering, why aren't you alert and awake like you used to be, Russ? And so the idea got for automating the whole thing. And I met Lou Boyd, I think, and this in our picture up here on the there. That's at any rate, we decided we just automate it. He was working on it, and we worked together, got his 10-inch telescope working first in Phoenix, and then 6 months later, I got one working back. I lived back in Ohio at that time. That's this telescope here. Can you see the pointer all right, Ed? Okay, Frank is nodding yes. Okay, so anyway, the thing that's kind of cool about this was, so this mount here was actually made by DFM Engineering. It was a prototype for a production mount for 16-inch telescopes, and at any rate, he gave it to me, and the OTA was me donated it, and the photometer was Optech's first SSB3 photometer, and Jerry Persia donated. So it was a donated telescope, but fully automated and worked great. The biggest problem was the weather, and Ohio wasn't really good for. At any rate, we started holding meetings. Doug Hall and I formed the IAPPP, which is the International Amateur Professional Photometry Association, and I started organizing meetings down here. This was the last meeting in Ohio, so this was like 1984. That's Frank Melsheimer, and that's his wife, Katie there. And so this was lots of both professional astronomers and amateur astronomers that had gotten interested in robotic telescopes. So I decided, needed to move where the weather was good. So that was Arizona. And it turns out the lab I worked for, Wright-Patterson Air Force Base, had a branch at Williams Air Force Base east of Phoenix, Arizona. And they developed flight simulators for fighter pilots. And I'm a pilot, and that looked like a fun job, and it was. So I moved to Arizona. And once Lou and I got our telescopes automated, the National Science Foundation was interested. They offered us money, and the Harvard Smithsonian Center for Astrophysics, the Smithsonian had a facility up on Mount Hopkins, and they still do, south of Tucson there. And so at any rate, we made a deal with them. We would make observations with my telescope for one of their programs, and they would give us use of the facility for 10 years. And that was a very good deal. They provided not only facilities, but a vehicle to go up and down the rough mountain road and so forth. So there's Lou and myself. So this is 1985. So it's what, 40 years ago. You can see this is the multiple mirror telescope at the summit in the background. That was when it actually had multiple mirrors. And this was our first 3 telescopes. This was the my telescope from Ohio. This was Lou's telescope from Phoenix. And this was a DFM Engineering 16-inch, one of their production telescopes. And it was for a grant for Doug Hall. So this is Doug Hall. He was a real mentor to Lou and I. And we discovered lots of new eclipsing binaries with spots. That was his thing. It was a real workhorse. And over that 10 years, we not only automated the entire observatory, but we added 4 more 0.8 meter telescopes. And so to pack them in, we actually had to choreograph, if one telescope came into space before the others, it kept the space so the telescopes wouldn't run into each other. And during the 1980s, towards we had to we lived 4-hour drive away, so this was a long ways away, and it took us about a year before we were willing to just leave the telescope run, the observatory running on its own. And I remember when we drove off and left it one time, it was not many days later, we got someone called in. They said, well, they were driving past the observatory. They saw the roof rolling off and rolling on, rolling off, rolling on. So we called down and had someone turn things off. Anyway, all the bugs were eventually fixed. And the last thing we did was we were gathering data for months on an end, without reducing them, and just hoping that things were going well. And so we made it so anyone using the telescopes, and they were shared by lots of different users, they could come in on the real high bandwidth 9600 baud modem of the era, and they could change the target list of what they wanted to observe, and then the next morning automatically the photometry results would be sent back to them. So that was kind of the first robotic telescope farm and the first remote access. And it worked well. And the word got around, and so we started holding meetings at the Lazy K-Bar Guest Ranch, and it's northeast of downtown Tucson, up in the hills there. And every February, and the people would come and get a tan and around the pool and ride horses over. But we discussed robotic telescopes and how to improve automation. And we always went up and visited the array of telescopes up on Mount Hopkins. And back in those days, before the internet and all that, the main way you communicate things was through publications. So there were more than a dozen books published, and the conferences grew to be fairly popular. They always filled up. So this is one of the last years here, gathered by swimming pool. Quite a few well-known astronomers like that. That's Alex Filipenko there. And Alex wanted one of our telescopes for use at Lick Observatory for Type 1a supernova. He was involved in the Type 1a search in the 1990s. And so we built him one of telescope. It's still at Lick, still working, I guess, 40 some years later. And he used it to he would look at about 1,000 galaxies a night and look for Type 1a supernova. And our telescopes. So I retired from the Air Force and moved on to other things in the early 90s. So in the late 90s, one of the robotic telescopes, Bill Barucki and I, in the early 90s, we talked about using robotic telescopes to observe exoplanet transits, and so Bill wrote the math for what's the probability of exoplanet transits, and I wrote the part of the paper on how to use robotic telescopes to observe them. Well, that never worked out to have a big global array just for this, but Bill Barucki went on, of course, to do a space telescope, do this, did a good job. But in 1999, after I'd left the observatory, Greg Henry and Lou Boyd, they did observe the first exoplanet transit, same one that David Charbonneau observed anyway. They have simultaneous published papers. So I decided to retire early, retired when I was 50, and took an early out, slightly reduced retirement. And my first retirement thing was to get a PhD in astronomy. And so that was actually a retirement hobby. So I'm actually still an amateur astronomer at heart. PhD was kind of necessary if you're going to teach astronomy. So it was fun. I really enjoyed the program. But then astronomy is a little bit of a disease like malaria. It never goes away. And so after doing other things for a while, I got interested again and built up a backyard observatory. And then me and a few other folks started a thing called the Altaz Initiative. It's not real well known, but it's been going now for 17, 18 years. And we meet every summer at Dan Gray's Sidereal Technology Factory in Portland, Oregon. And it's essentially kind of like those of you who know the Riverside Telescope Makers Conference. It was a lot like that. So it's essentially engineering, software geeks getting together to push telescopes and instrumentation. And so anyway, one of our missions was to our robotic telescopes that amateurs developed have been picked up by the professional astronomers by then, and we were kind of interested, so there was kind of a tech transfer from us to them. We were kind of interested in seeing if we could get a tech transfer in the other direction. So this would be from mountaintop robotic telescopes down to small amateur telescopes. So we started going to visiting mountaintop observatories and talking primarily to the engineers that designed these and kept them running about their advanced technology. And so they had, these were very expensive one-off telescopes. They could design and just built one of them. In case of Gemini, they actually built two. But and what we were interested in was small telescopes that could be, more mass produced. And so on the upper left here, that's Dan Gray from Sidereal Tech and myself. They were over the Subaru 8-meter telescope, and that was really especially interesting because it was direct drive, no worm gears, which are always a pain, no backlash problems, just all it was it's all a computer and high precision Renaissance encoders and so Dave Rowe, who's the chief technical officer now of Plane Wave Instruments, we decided we'd build a Altaz telescope incorporating some of this technology. So here's one of our summer meetings up in Portland, Oregon. And this is a direct drive motor. And so Dave Rowe wound the coils in his garage, and so we assembled this motor on plywood. So there's it's a little hard to see, but there's magnets up above here. And then Dan Gray built this controller for the motor, and it has Renishaw encoders around the edge there. At any rate, it worked well. And so I was teaching at Cuesta College and Cal Poly at San Luis Obispo at the time. And I had a couple of mechanical engineering teams develop a telescope. And so we scrounged up all the parts, including an 18-inch mirror that Tong Lu at Hubble Optics contributed. And at any rate, one team built the OTA, and the other team built the rest of the telescope, including direct drives in both RA, well, in ALT and AS. And so that led to the Plane Wave folks, Dave and Rick Hendrick and Joe Haberman, their optician. They came to the critical design review that students had, and we got to talking afterwards. Could we produce? Could Plane Wave produce this commercially? And at any rate, kind of the back of the napkin thing. How much would the parts cost? And at any rate, the answer was yes. And so Dave Rowe led the team, and it took them a couple of years, but they kind of went from what we call the Cal Poly 18 telescope to the CDK 700, and then Dave continued on another couple of years and came out with the 1 meter plane wave telescope, which is I think it's the ultimate perfect size production research telescope, and it's kind of affordable for rich amateurs. And I went on after that. I was and for several years kind of pushed to see if we could kind of reverse technology transfer from large space telescopes to mass production small space telescopes. And we held a number of American Astronomical Society workshops and other meetings and so forth. And at any rate, it hasn't happened so far, but hope springs eternal. So we moved from Arizona to California, where I taught at Cuesta College and Cal Poly. And I wanted to teach an astronomy research course in the local community college, Cuesta College. They were agreeable to that. I was teaching introductory astronomy, and so we started teaching this. And to start with, we did variable stars, and so this was CCD photometry of variable stars. But the problem was it took so long, to get a clear night, and if it was a longer period variable, we needed several nights and lots of data. It was just beyond the students, and we worked all semester long, and they wouldn't be finished, and I would have to try to finish up paper. So we switched to observing double stars because they were a lot simpler to do, and you could get your observations in one evening. So binary stars were discovered by William Herschel. Here he is with his sister Carolyn, and he started observing binary stars in 1781, really hoping to see a parallax shift between bright and dimmer stars. So he thought the dim stars was further away, and they often were, but often they were not. They were actually binary pairs. And by 1803, he published a paper on 25 of these he had found have a curved orbit, and so he called them binaries, and that's where binaries came from. But it's two stars rotating around a common center of gravity. And we can apply Kepler's laws. And the first law tells us that it's an ellipse, and it's an ellipse not only face on, but if you rotate it around anyway, an ellipse still stays an ellipse. But the problem is you really want to kind of know what it is face on. So you can use Kepler's second law, equal errors and equals time. So if you know the separation between the two stars when you observe them and the position angle with respect to celestial north and the date of observations, and you get a bunch of observations over time, often it's decades or even centuries, you can put this all together to reconstruct the orbit and get it face on, a little fancy math. And then Kepler's third law, so it's relating the period here, period square, to the semi-major axis cubed. Well, we've got the period nailed down, and we have the separation between the stars, and we have the semi-major axis of the orbit, except it's in angular units, and we need them actually in physical units. But if we know the parallax, so we know the distance of star, we can convert it to a actual physical distance. So that gives you that term. And then this is the sum of the two masses. So if we want to know the mass of an individual star, which is what observing binary stars this way is really good for, you have to parse the mass out, and you can do that by getting radial velocity curves. And so, of course, by then we knew the gravitational constant. So to make a long story short, we can use over time a bunch of observations of binary stars, just getting position angles, separation, and date, get the parallax, and then get a radial velocity curve, and out pops the most accurate masses for the individual stars that we get. And of course, that's really important for stellar evolution. And so, astronomers, there's lots of these stars that are either known to be doubles, and you want to refine their orbits and get better periods and better semi-major axes, or they might be, and you want to keep observing. So at any rate, it's turned out to be a great thing for amateurs to do. Professional astronomers just didn't have the time to keep up with all of them or do them all. And they did lots of this during the 1800s. It was a really big deal. But in the 1900s, astrophysics and spectroscopy and bigger telescopes kind of took over the interest of professional astronomers. And so lots of this shifted to amateurs. And the U.S. Naval Observatory, they kept track of all this in the Washington Double Star Catalog. So, and what they do is they glean all the published values for double and binary star position angles, separation, and dates, and any published orbits, and they keep track of it all. And but in order for it to be included in the Washington Double Star Catalog, the observations needed to be published. And so there sprung up a little international cottage industry. There's about 6 journals in the Journal of Double Star Observations. The U.S. specializes in publishing professional, amateur, and student observations of double and binary star. But there's one in Britain, there's one in Russia, the Italians have one, and so forth. And so I started a class for research class for students, and we started out using an astrometric eyepiece. So this is just an 1.25-inch eyepiece, 12 millimeter focal length, and it has a reticle in it. You can measure distance between the stars, and the protractor you can measure the angle with respect to celestial north. And you can do this, and you need a stopwatch and turn the telescope drive off to calibrate it. And but anyway, you can gather 10 observations in 10, 15 minutes. And students can do it. They're watching the actual stars through the eyepiece. And anyway, it turned out well. And so we had lots of published team papers. Of course, the stars had to be pretty wide and pretty bright. And so the educational value was high, the scientific value was not zero, but it wasn't real high. It wasn't the most interesting. It was the, if they're white and bright, they have long periods. And so anyway, but it worked well. Here's we started doing ones in the summer. So normally we take all semester to do, but this summer was a long weekend. We geared up so we could actually observe stars, write up papers, and get an external review. People standing by on the internet, all in a long weekend. Very, very busy. And eventually the observations, instead of students making in with telescopes supplied by and operated by amateur astronomers, we started using lots of our students' courses use Los Commerce Observatory, their 0.4 meter telescope. There's one of theirs. So you could just request that. And that's what we still do. So the problem was, I got into, well, this is great for education, but if we want to do cutting edge science, we got to go dimmer and we got to go lots closer. Well, the problem is to go close. You really want to get below the seeing limit, and so Anton Labre, a French astronomer, in 1970, he published a paper where he had taken a high-speed film camera and an image intensifier and put them on the 200-inch telescope at Palomar and did what's called speckle interferometry. So this little cartoon here. So the light comes in and it gets spread out by the different mirror cells into a whole bunch of speckles. And this is what you'll see at high speed if you really magnify an image. Well, but it turns out that if there's two close stars, they get spread out, but if you're within what's called the isoplanar patch, which is about maybe 10 arcsecs, not very big, but it's big enough for double stars, that image of the double gets spread out, spread all over the place, and you can essentially recover it by using a Fourier transform and some fancy math on a computer, and you get the image back. And Hal McAllister, and I found a nice, he's now retired, but I found a picture of him shortly after he was a postdoc at Kitt Peak. So when he was a postdoc at Kitt Peak, he realized that the astrometry with longer periods, stars are moving slower. And so at that time, they weren't moving fast enough to get radial velocity. So you had a bunch of stars that we knew their orbits, but we didn't have the radial velocities. And they were long periods. We had a bunch of short period, fast moving stars. We knew the radial velocities, but we didn't know the orbits. So you couldn't get the two together to get the individual stellar masses. And so what Hal did, he says, speckled interferometry will do this. And so on the 4 meter telescope, and here's what they started out strapping themselves in the cast cage on the 4 meter with a camera. So they would, and actually just using high-speed film. But as soon as microcomputers came out and CCD cameras, they use this. So this is actually image intensified CCD camera here, and then this is the optics and filters wheel. And this is myself. This is Brian Mason from the U.S. Naval Observatory, and this is one of my star students. Anyway, this is back quite a few years ago on the 4 meter telescope on an observing run. I wanted to see how they do speckle interferometry. And by then, there was what's called image intensified CCDs, and there was one available for $14,000, and I got the AAS as a grant. And so here's that camera, and got it half price from the manufacturer. And we put it on Los Telescope. This is on Dave Rowe's facility out in the Mojave Desert. This was the plane wave instruments, their very first OTA, a 1/2 meter one. And we've stacked a couple of Barlows on to get, take advantage of the full resolution of the telescope and this EMC CD camera. And it just worked wonderfully well. Our first night, we got 40 close binaries, and out of that, we discovered 2 new triple stars. Anyway, we were just totally thrilled, and it just works great. And so we were now we caught up with professionals in terms of what they could do. And so we actually put in competitively a group of amateurs. And by that time I had my PhD. So and I called myself a professional and got Brian Mason. At any rate, we applied for time at Kidd Peak. We got 8 nights in the fall of 2013. And so, and here's Speckle. So this is actually on, this is what speckled interferometry looks like. And you can see all the speckles there. And then Dave Rowe wrote a program called Speckle Toolbox that would do the Fourier transforms and then do a thing called bispectrum analysis, which reconstructs the phases. And out pops an image, and it is an image of sorts. It's mathematically reconstructed. But you know, there's a star, so that the semi-major axis across the star here is half an arc second. Well, so you know, so it's semi-made half, and the full. This is 1 arc second. Well, that's well below the seam limit most of the time, and so here's that distance there, and that our observation is right there. At any rate, to explain this diagram, these little green pluses, these are all visual observations. So these were mainly like the Lick 36-inch telescope. They did lots of visual observations with a filar micrometer. And you can see that, you know, they were kind of all over the map. And it was just because this is too close. So even a good scene at Mount Hamilton, they were really pushing it. And so the observations, this is about a 40-year period. It's going in this direction. And here we start having the first speckle observations. That's the Hipparchus space in 1991, the space satellite. And these are more speckles here. And this orbit in black was published right here. This is Bill Hartkoff observing on the 100-inch at Mount Wilson. But at any rate, after this orbit was published, Tocqueville and a few others, they observed, and you can see it was going off track. So we put it on our observing program for the Mount Wilson 60-inch in 2023 in the summer. And there is our observation. So we compute, you compute a new orbit, the period's different, semi-major axis different, and you can get a much more accurate stellar mass out of it. And so hopefully this will work. For quite a few summers now, we go first to the Society of Astronomical Sciences meeting. It's usually Friday and Saturday in Ontario, California. And there's Bob Buckheim. He's the president of SAS. And we would take our students, and it's mainly amateur astronomers. You can see mainly older amateur astronomers. Anyway, lots of good papers on both equipment and techniques, but also lots of science they're doing in lots of different areas, including spectroscopy. And then immediately after, on Sunday afternoon, we would head up to Mount Wilson and observe on the 60-inch and sometimes on the 100-inch, sometimes on both. And so at any rate, we've done that for a number of years, and it works out really well. And hopefully this will work. Let's see if we can.
In June of 2024, a dedicated group of students, educators, and amateur astronomers
I don't hear any
took part in
sound.
the Society for Astronomical Sciences Symposium and conducted observations using the 100-inch and 60-inch telescopes.
I'll try one more time here. Share.
We were hearing it, Russ.
Oh, you were hearing. Okay, let me
Yes.
just go. It's just that I can't hear it, which is fine. Thanks, Ed.
Unmute it, they say. That's right. That's right.
Ed, are we back all right? Frank, can you hear me?
We need to stop the video. Stop the
Yeah,
sound.
can you hear me all right, Ed?
Yes, we can hear you now.
Oh, okay, good. Yeah, thanks. So recently,
The Trump administration's
during known
self-styled
binary
Secretary of
stars, we've
War,
been
Pete
observing,
Hegseth, has spent most of the
follow-up
week on
from
defense,
Gaia.
facing accusations that he
Russ,
committed
YouTube is
war
still
crimes
active.
and that he endangered the lives of U.S.
Say again,
pilots.
Ed?
At the Pentagon, it seems to be
have to
all
close
turmoil
YouTube.
all the time. Next.
Oh, okay.
This is Washington Week with The Atlantic. Corporate funding provided by...
In 1995,
Just close that tab.
Yeah, there we go. We back on track now?
You're good. We're back.
Okay, good. So there's a bunch of big space and ground survey telescopes that have kind of taken over the role of some of the things that small telescopes used to do. And in the case of astrometry, and binary stars, things like that. Gaia has done a tremendous job on, they've observed like 2 billion stars and have parallaxes and so forth on most of the stars, but it turns out that some of the stars, a nearby companion star confuses Gaia, and so they see it as one star, but they know something's wrong, and so they don't report all the parameters. And it turns out we can observe these stars from the ground on 1 meter class telescopes and discover new binaries, and so that's what we've been doing recently. And so I'm running short on time, so let me kind of skip ahead here. Let me introduce Frank. Frank Suits is joining us from Australia, and he's got a PhD in optics from the University of Arizona, so he knows Tucson well. Worked for IBM for many years. And Frank, if you could tell us about speckle cap.
What's Frank's last name?
Suits. He's just muted. I can see him.
Yeah, we've got to unmute him.
Oh, okay. You have control.
We're getting there. Jim assures me.
Yeah, no problem. And Doug Walker,
Okay,
if you can
now he
unmute
can
him.
unmute.
Okay, you can unmute now. There we go.
Great. Thanks very much. Yes, I have very fond memories of Arizona, Tucson from the 80s when I was there for 5 years. So I've been back a few times, but it's great to make a connection there again and to meet you all. So I'll just briefly summarize. I know it's running late, but Russ described some of the technology involved requiring to take the video that you need of these short exposure speckle images. And it's a lot of things are designed for deep sky imaging, but there's not as much designed to make it easy to capture high speed, high frame rate video. So I created an environment just over the last year and working with Russ and all the other people involved in the Mount Wilson observations to have a client server environment that just allows control of a telescope and pointing at selected targets and then capturing video, all with an interactive video environment that's web-based. So this hasn't been formally released, but it was used recently successfully at Mount Wilson in October. And so I will be formally releasing it at some time, but the intent is to make it easy to use for students but also to take high quality scientific data. And a key thing that makes it fun to use is that it has live Fourier modes that let you see a double star that normally would look like a blob of speckles, and you can't really tell it's a double. But when you view it in this live Fourier video mode, you can see these fringes that indicate that it is a double. So during the observing session at Mount Wilson, these were double star candidates, so you don't know if it's a double star or not. You see the live video speckles and it doesn't tell you much, but then you turn on the video mode and suddenly you see fringes and you know it's a double. And so that for outreach and working with students, it was a very satisfying experience for them to make these discoveries in real time with this approach. But I'll stop there but this is available on the web. It hasn't been formally announced, but I expect I will formally announce it somehow soon. Thank you.
Yeah, thank you, Frank. Let me get the slides to advance here. So we have a new community college in Arizona, just started this fall, Gila Community College. And a Doug Walker, and if, Ed, if you could unmute Doug Walker, appreciate it. Any rate, Doug and I are on the staff teaching astronomy, and this is our schedule for the courses.
Doug can
And when
unmute. I'm sorry, Doug can unmute now.
Oh, he can't. Okay, that's all right.
No,
I'll just do
he
it for him.
He is able to
Oh.
unmute.
I am
Okay.
unmuted. Yes.
Yeah, and so Doug teaches 3 of the courses, and I teach 2 of them, and so and they're in person plus online. So Doug, why don't you tell us about your
Sure. Yeah. Thank you, Russ. Good
three
evening,
courses.
everybody. So, yeah, Doug Walker here. I met Russ back at the SAS conference early 2000s. We've kept in touch over the years. Kind of followed Russ in his career because I took an early retirement from Lockheed Martin here in Phoenix, Arizona, is where I'm located. Back in 2013, went to the University of Canterbury, New Zealand, got my PhD in observational astronomy down there and photometry of variable stars and clusters and such. So follow up on what Russ was saying. Yeah, the Gila Community College, we're starting up a series of courses here. We hope will be unique as far as what community colleges will offer. For the spring here, we're going to introduce, or I'm going to be conducting 3 separate courses. One is just a general introduction to astronomy. And this kind of follows your general astronomy course, which I do teach online also for another community college here in Arizona. I've taught also in person over the years. So that's just, again, 16-week course. It fulfills the science requirements of 4 credit hours for general studies for students to transfer to universities and such for their science requirement. 3 hours lecture, 1 hour credit. We have labs and such in there. And then the other 2 courses are the AST 131 is an introduction to astronomy research. And this follows on the heels of what Russ has been talking about. He's been doing for years, except we're going to take a little bit different bent on this one. It's going to be an exoplanet. So it's going to developing kind of a parallel track to what they've been doing as far as binary stars, except this will be to focus on exoplanets. If you go check the, NASA website or whatever now, there's like over 6,000 exoplanets they've discovered since the 1990s. So the objective of this course and the scientific objective is to refine some of those orbits and stuff, those exoplanets. So there's lots of targets out there for us. We're doing the same things we're doing with the binary star type works, except we're going to apply it to exoplanets. So this is like a shorter credit course. It says 3 credit hours there. It's either 2 or 3 credit hour course. It's also in person and Zoom sessions. I'll talk about that in just more in a second. The third course is the a binary star system. So this is in conjunction with Paul McCullough's course that he does at Colorado Mountain College, and they do I believe it's a in-person and our Zoom type course there, where they basically do the student research into binary stars and such. And so students get a published paper in the JDSO at the end of that. We're going to do the same thing with exoplanets. Now, what makes this unique than previously is that we've set this up for a long weekend there in Tucson, and you can see the dates at the bottom there, March 20th through 22nd. We're all going to meet, and the target is this El Conquistador Hotel there in Tucson down there, Hilton Resort. We're going to meet there. Students can either stay there. People coming in can either stay there or stay where other place they prefer. But we're going to meet there for a couple of days, join together as a group, and then we're also going to, from there, we're going to take a tour of the University of Arizona, the Mirror Lab down there. We're going to get a backstage tour of that. We're talking about doing a planetary session there. We'll have a day of a conference from speakers and stuff. We'll bring in talking about different aspects of amateur professional astronomy. And then one day we're going to go out to Kidd Peak National Observatory, do a tour there, and then go into the early evening. We do the night observing down there. So it's kind of exciting that, we're mixing up the classes where now students just, you don't have, if you're taking it, again, for the introduction to general astronomy, you're trying to get rid of your science requirement because you're a journalism major or something like that. Well, this will give them an opportunity to do something fun, right? Visit some courses and such, And same thing with the exoplanets and the binary star system. So we're hoping this will be a hit with both students, even professional astronomers might want to do it, amateur astronomers, anybody is welcome. I think I'll pass it back to Russ.
Yeah, thanks, Doug. Yeah, and the Gila Community College, no discrimination in age, and students over 55 that are residents of Arizona, the tuition is free, and the college appreciates they're trying to build up their student body. So this spring, I'm going to teach the advanced research course that we've been doing at Mount Wilson. And Mount Wilson's great for late spring, summer, and early fall, but winter and late fall, early spring is not a good time to observe Mount Wilson. So I've been looking for somewhere else to do these observations, and our 0.8 meter telescope out at the at the dark side, it's really ideal for speckle interferometry. So it'll make a great instrument, and the club has agreed to kind of join up with a partnership with Gila Community College, and so we're going to be offering there'll be some online sessions in advance. Wednesdays at 7 p.m. to work up the target list, and then the observations will be made March 18th to May 6th. It's not during dark time, but speckle interferometry just isn't bothered by moonlight, and we'll be just observing Gaia 2 parameter stars looking for new binaries. So we should have a slew of new binary discoveries. And then after the run down there, we'll continue meeting on Wednesday nights to work together as a team on a single paper to publish our results. So at any rate, that's the presentation. Sorry for running a little overline, but so this kind of, you can see how really a bunch of amateur astronomers have worked with professional astronomers to, develop things and then work with students. And the students really appreciate it. We've had over 200 team papers with students and amateur astronomers as co-authors. And it really boosts the students' careers. They get scholarships and it builds their confidence, and to actually be published scientists early on. So anyway, that's the presentation.
Thank you, Russ. Stay with us here for a minute, Russ.
Okay.
We'll raise the lights and see if there's any questions, first of all, in the room. Let me just say, what was the tuition for those classes again, for those over 55? Because I see one or two of them in the room here that are over 55. What was that?
Yeah, there's tuition is free, but the college still gets paid for by the state for what's called full-time student equivalents, footsies. And so yeah, if you're over 55, sign up for any of these courses, and there's no tuition charge. There is a small lab fee to pay for miscellaneous expenses on an in-person meeting, but it's not very large.
We've got a question in the back. We've got to get the mic over there, so it'll take a moment.
Hello. I just wanted to tell you how funny it was to see that Radio Shack in the very first slide with the telescope for $499. Did everybody see that Radio Shack? Anyway, that was funny to me. The other thing I wanted to ask you was the music, the viola violin music. Can you tell me who that was?
Yeah, I can't tell you, but Michael Ellis, the physics high school teacher at Payson High School, filmed that, and he selected the music that went along with that. It gets livelier as it went. I liked it.
Go ahead, yes.
Yes, Russ mentioned many aspects of his impressive career. What part of his career did he find the most enjoyable?
Well, I think the teaching part, well, I enjoyed my research and development. So that was a quarter century as a research and development supervisor, and that was lots of fun. And I particularly liked the development of flight simulators for fighter pilots. So the Tucson National Guard has an F-16 squadron with back seats, so we got some backseat time flying out of F-16. But in terms of astronomy, the initial development of the robotic telescopes and observers, it was lots of fun, but it was stressful too. That was lots of work. And I lived up in the Phoenix area, and it was a long drive there. And so vacations and so forth were spent down on Mount Hopkins. But I think I particularly like teaching at Cuesta Community College in person on the early research courses when we were exploring, how can we do this all in one semester and get several team published papers. That was particularly enjoyable.
I'd like to ask a question. How do you get a group of students to put together one publication? Is there a primary writer, but everybody gets their name on it, or how's that work?
Oh, that's an excellent question. So it turns out it took us a few semesters to really get the hang of it. And what we learned was the way you do it is you do it just like other scientists do it. So you don't have every student do everything. Some students are better at writing, some are better at computer analysis and so forth. And some students have lots of time and are eager beavers, and the other students, they're busy or they aren't interested and don't have much time. So there was this widespread, but science has a very easy answer to this. It's called author order. And so the students that did the most work and led the charge, they were the first authors and had special responsibilities to see the paper through. If it wasn't finished at the end of the semester, they were on the hook for helping finish the paper. And so division of labor, you can't keep telling the students, this isn't a class. This is a research project, and when it's totally different rules. We follow the rules of scientific research and not the rules of classes and education.
How about online? Do we have any? Nothing on Zoom. Okay, I think that's the questions that we've had. Russ, thank you so much for joining us from Hawaii.
Yeah, thank you, Ed, and I enjoyed it, and look forward to the observing run in April.
It'll be a lot of fun. All right, thank you much. Now, I think Eric is here with us. Eric, do you have a report for us this month? Eric does our planet report. We'll see what's new and different in the sky.
Yeah, I just had a thought about the beginning of this evening when we heard about constellations that were created 3,000 years ago. If we go back to that time, we would see the same constellations. We could point our telescopes to wherever we want. But if we go 10 times further to 30,000 years ago, we would be lost because many constellations are just not recognizable since the stars moved. But those 30,000 years are less than 1/100,000th of the time that life was on Earth. So since life was on Earth, constellations had to change 100,000 times. So, but now we can see what's in the sky this month. And so Saturn is the evening planet. Its transits 7 p.m., late on the month 6 p.m. So ideal for early evening observations. The the rings were just at the minimum opening angle at the end of November. So now they are almost the same, still 0.2 degrees open. That means it's really a line in a telescope. But by the end of the month, they are 0.7 degrees open. That's so more than 3 times as far, that they'll be more than 3 times as bright than now. So they will be changing within a month quite a lot. But even at that opening angle, it's still only half arc second wide. So they still look like a line. It's just a much brighter line. And during this time, when the rings are aligned, all the inner satellites move in the same line. So they just go back and forth. They usually they go in an elliptical orbit around Saturn. And the Iapetus, the furthest one out, that's just south of Saturn today. And the other 4 or 5 moons of Saturn that you can see in a telescope, they just move back and forth. Titan, of course, is the easiest visible. Then 3 degrees east of Saturn is Neptune, the first planet here in our system. And it's going to its conjunction on February 15th, when it will be only 1 degree from Saturn. And so that happens every 35 years. This one will be the closest one. The next one you can see in 35 years. Then Uranus, the planet in between those two, Saturn and Neptune, is just right now 4.5 degrees south of the Pleiades. So if you put the Pleiades on the top of your binoculars, then probably Uranus is just at the bottom one. And as the closest approach between Uranus and the center of the star cluster is just at New Year, where it's 4.4 degrees. And then we'll be as close again in 84 years. Jupiter rises around 8 p.m., so it's up most of the evening now, later in the month, 7 p.m. It's close to Pollux, so those Pollux cluster and Jupiter form a kind of arc right now, but that moves as Jupiter is moving in the sky. Its opposition will be early January. So right now it's already close to the maximum diameter of 46 arc seconds, and you can see nice details on Jupiter. And from the inner planets, we only can see Mercury. So the planets that are usually easier to see, Venus and Mars, are not visible. They are behind the sun. And Mercury is visible 5:30 to 7 a.m. or so. But best around 6:15 or 6:30. And this is as good as Mercury can be visible. It's 20 degrees above the sun. That means it rises before astronomical twilight starts, and it gets reasonably high before it gets somewhat light. So that's about how good Mercury can be visible. And for the whole month, it has a constant magnitude, even though Mercury races around the sun so fast, and it's moving away from us. So it would be fainter, but at the same time, the phase increases, and both things just compensate each other perfectly, so the magnitude stays constant. Then the first time after the new moon will be visible on the 21st of December. That's the first day of winter. And then 10 days later, on New Year's Day, we'll have the highest full moon. It will be 86 degrees, 86.0. There was one full moon a year ago, 85.9 degrees. So that's really the highest it can get. And for the next 9 years, those highest elevations will go down 10 degrees because of the lunar orbit. So in 9 years, the moon never will get higher than 7 degrees here. But then 9 years later, it will go up to the same value that we have now. So thank you very much.
Thank you, Eric. All right, I think it is probably time to say goodbye to our friends on social media.